All right, Falcons, we are in chapter 22. This is the last chapter of Unit 5. So we are going to put together a lot of what we know, and we have one more time, just a little bit of homework to do. With our objective for this chapter being students test null and alternate hypothesis about two proportions. And so in the real world, we're much more likely to make comparisons between two values, as we've kind of seen in a couple of the examples in class. And these two values, either proportions or means, then we are to investigate the validity of just an isolated value. And let's be honest, we're much more interested in comparisons. Do you really care how good your test score is, or would you be more interested in your score compared to the rest of the class? So who won the Super Bowl? You don't just look at the one team's point totals. You compare the two and see who is better. So more often than not, we want to know how two groups differ. Is treatment 1 more effective than treatment 2? Is a treatment more effective than a placebo or a control? Is my group better than your group? Who is the best baseball player of all time? Hint, my opinion, it's Willie Mays. So to examine the differences between two proportions, we will use another standard deviation, the standard deviation of the sampling distribution model for the difference between two proportions. Remember, standard deviations do not add, we add the variances, which is standard deviation squared. The variances of the sum or difference of two independent random distributions is the sum of their individual variances. Remember, this is like the Pythagorean theorem of statistics. So what we will do to find that standard deviation, so the proportions observed in independent random samples are independent, thus we can add their variances. Sorry, I needed to add that caveat. So we take the standard deviation for our sample proportion 1, P1Q1 over N1. We take our standard deviation for our sample proportion, which is P2Q2 over N2, take the square root. So we square both of those. These are the variances. And then if I want to find the difference in the proportions, or the sample proportions, it's the square root of the sum of the variances. So P hat 1 minus P hat 2 is the sum of the variances. So it all follows that standard error then is P hat Q hat over N plus P hat Q hat over N. Okay, we use standard deviation for the sampling distribution. We use standard error when we're centered around the sample proportion. That's the difference between the two. So what else have we done when we're checking this? Well, it's our independence assumption. Old news. We're looking for randomization, so the data in each of the groups should be drawn independently and at random from a homogeneous population or generated by a random comparative experiment. We're also looking for the 10% condition. If the data are sampled without replacement, the sample should not exceed 10%. So either it says without replacement, then we have to check for 10%, as we have done previously. The new thing that I want you to know, so this is new, independent groups assumption. Not only are the samples independent themselves, the two groups we are comparing must be independent of each other. We don't want these two groups to be mixing because then it adds in other conditional probabilities that we want to avoid. Next, we check our sample size condition. So the success and fail for both groups are big enough that at least 10 successes and 10 fails have been observed in each. So it's not good to just check one, we have to check both groups. So we already know that for large enough sample sizes, each of our proportions has an approximately normal sampling distribution. This is the same, or the same is true, of the distribution of the differences. It's also going to be normal. So once we jump to the normal distribution, provided the sampled values are independent, the samples are independent, and the sample sizes are large enough, the sampling distribution, P1 hat minus P2 hat, is modeled with the normal model with our mean, right? We're going to do, our mean is the difference in the proportions with the standard, with the standard error, the square root of the sum of the two variances. So think about that for standard error for a moment. It is the sum of the variances, which in effect weights the standard error of the difference distribution. It's adding in more variables, so it's increasing our variability. So when the conditions are met, we're ready to find the confidence interval for the difference of two proportions. The confidence interval, as you remember, is our sample proportion. So in this case, it's P1 hat minus P2 hat, plus or minus our critical value, that's still our z-score, and then our standard error of our difference, which you see here. Note that the confidence interval is about the statistic P1 hat minus P2 hat. It's the difference in the sample proportions. As always, the critical value is determined by the desired confidence level C, and you know how to find that with inverse normal. So for a two proportion confidence interval, on a TI-84, you're going to hit stat tests, and then you're going to go to two prop Z interval. And for a two proportion Z test, you're going to do Z test. Now note in both these conditions, X1 is N times P. Well, that would be P1. And then X2 would be N2 times P2, because our sample sizes are different and our sample proportions are different. Looks oddly familiar. So let's actually do one of these problems. So we sample students attending various colleges and universities to see how many plan to go to Florida for spring break. 5,690 of the 12,931 randomly selected male students indicated they had plans to go, while 1,051 of the 3,285 randomly selected females indicated intentions to go. Find a 95% confidence interval for the difference in the proportions of males and females intending to behave like idiots during spring break. And I'm glad we are bringing this up, as spring break is only a couple weeks away. So note, we have these two proportions. Let's call this P1, and then let's call the females P2. We actually went out and collected this data, and we want to build a 95% confidence interval. So what are we saying here? Well, the P1 hat is 0.44 and P2 hat is 0.3199. I want to compare these two groups. Okay, so we look at our two proportions and we're building a 95% confidence intervals. First off, let's check our assumptions and conditions. Male and female students are randomly selected from the university, so we're good with random. We will assume that the intentions of students to go misbehave are independent. The two groups, male and female, are also independent. So now we're going to check our successes and fails condition. So we have N1P1 is 5690. That's definitely greater than or equal to 10. N1Q1, definitely greater than or equal to 10. And then for our females, 1051 is bigger than 10. And the opposite, 2234, is also greater than or equal to 10. So we have enough successes and fails in this. And then lastly, 12,391 males and 32,855 females are less than 10% of the population of college students, provided, what is that? Around 15,000, provided that there's 150,000 people that go to college across the country. That's safe to assume. So we're going to conduct a two proportion Z interval for the difference in proportions. So we are going to go to our calculator. And let me pull this up for you all. On our calculator, we're going to hit menu. We're going to go to statistics. We're going to go to, confidence intervals. And we're going to go to a two prop Z interval. Now we're going to type the number of successes in, which was 5690 for the male and 12931 for the sample size. We have 1051 for sample 2, and we have 3285 for the females. We want a 95% confidence interval, so we hit OK, and we are given a bunch of information. So we have our lower, our upper, the difference in the sample proportions, our margin error, P1 hat, P2 hat, N1, and N2. Okay, back onto the notes page. We are going to write out our statement because this is as required. So we first write out, this is how we build our confidence interval. The difference in the proportions plus or minus z star times the standard error. So we have 0.4400 minus 0.3199 plus 1.96, because that's your critical value for a 95% confidence interval. We have all of our information in there, and then we're just going to fill the blanks in from our calculator. So we have 0.1201 plus or minus 0.0181, or 10.2% to 13.82%. And if we're finishing up our steps in Panic, I am 95% confident that the difference in proportions of males and females in attending to go to Florida for spring break will fall between 10.2% and 13.9%. This is talking about the difference in males versus females. Or since we wrote males first, males are more likely to go on spring break and act stupid than females in college, between 10.2% of the time to 13.9% of the time. Now, what's the flip side of this? And this is the challenge. A typical hypothesis test for the difference in two proportions is that there's no difference. So ain't nothing happening. Well, if there's no difference, then we would say that the null hypothesis for the difference in the two things is 0. Or if you prefer, that they're equal. I prefer writing this way, as in there's no difference. It's far easier to calculate. Since we're hypothesizing that there's no difference between the two proportions, we're assuming that the sampling distribution for the two samples is the same actual sampling distribution, which implies that the standard errors for each proportion sampling distribution are actually the same. And since we're assuming that they're the same distribution, we actually have to change something about our standard deviation. And so what we do, and this is the one thing I just need you to remember, in this case, we're going to pool the counts to get a more accurate overall proportion. So when you're running a hypothesis test, we are going to pool. With a confidence interval, we didn't pool. Okay? So the pooled proportion, or our p hat pooled, is just the sum of the successes over the sum of the sample sizes. So N1P1 plus N2P2 over N1 plus N2. If you've been given the number of successes for each sample, then it's just X1 plus X2 over N1 plus N2. If the number of successes are not a whole number, round them first. This is the only time you should round your values in the middle of a calculation when we are pooling. We then put this pooled value into the formula, substituting in for both sample proportions in the standard error formula. We are going to use this pooled proportion to find the standard error for the difference in our sample proportions. This is the only difference. Okay, so we then reject our null hypothesis if we see a large enough difference between the two proportions. How can we decide whether the difference we see is large? Same way we always do. We measure it against the standard error. Unlike previous hypothesis testing situation, using proportions, the null hypothesis doesn't provide a unique standard deviation. So we'll use a standard error. And so this is the difference here. We're going to use the standard error of the pooled sample for a standard deviation. So the conditions for the two proportion z-test are the same as the two proportion c interval. So we are writing our hypothesis, so we're doing our phantoms. We have our null, and then we would need to think of our alternate. We use the pooled value to estimate the standard error, which is from there. We now find our test statistic, so this is our z-score. So it's the difference in our sample minus our null, which, by the way, should be 0, which is pretty nice. So when these conditions are met and the null hypothesis is true, this statistic follows the normal model, P1 minus P2, which is 0, and the standard error for the pooled. Note that the model is about the difference in the population proportions, which we're saying is nothing, which is why it's far easier to use 0 than if they're equal. So we're going to do 2 examples in the last video, and then we are done with Unit 5. So thank you, Falcons. I will see you in the next one.